video is covering section 10.5, which is talking about the area of a polar region. So this is actually a typo here. Your note should say 10.5. Okay, so to find area in polar coordinates. Now, when we found an area in rectangular coordinates, that was represented by taking an integral from A to B. But when we find area in polar coordinates, we can't do that as easily. So with rectangular coordinates, remember we kind of sliced up our graph into rectangles, and so we had like this width by the height, and then we took an infinitesimally small width, which was dx. All right, so we're like slicing that up. Now, we're going to be doing the same thing with polar coordinates, but we're in a different polar system, or we're in a different coordinate system. So what I'm going to do is I'm just going to kind of draw a curve. Let's pretend that's in the polar curve, or polar graph. Okay, so some polar graph. I'm just looking at this first quadrant here. And so what I would do is, let's say that I want to take the integral. Now, when we're talking about polar, we're going from thetas, okay? Instead of x's, we're going from thetas. So let's say that I have this one theta, and that comes out here. We're going to call that theta A, okay? And then I'm going to go to theta B. We'll call that theta B, okay? So let's say that I want to calculate the area. Now, remember, as I'm moving across here, I have these radii that are coming out of the pole, hitting this graph. Okay, so if I found the area of this region, then I would be calculating what you see there in the yellow region. Okay, so we'd be looking for that area. So instead of slicing this up into rectangles, what we're actually doing is these are like sectors. So think polar, the natural graph in polar are circles. And so if we think back to an area of a sector of a circle, and it's okay if you've forgotten, but the area of a sector of a circle, which you probably learned in geometry, is 1/2 theta r squared. Okay, so the area of a circle is represented by 1/2 theta r squared. Now, what I'm doing is, if I were to chunk this up and I was to find each of these little sectors, okay, I've split this up into 4 different sectors. Okay, each of these little thetas here, pretend that I did this perfectly, and each of these thetas have like uniform width, okay? And I was to add up each of those sectors, then you would get that area. So what I just said, I said add up those sectors. So what you're going to end up doing is you're going to be adding up, so that is taking an integral. So I want to add up a bunch of sectors, right, which have area of 1/2 theta r squared. But what's going to happen is, as I add up a bunch of these sectors, I'm going to split them up into more and more sectors. And so instead of getting that infinitesimally small width of x, I'm getting this infinitesimally small wedge with theta. So we have an infinitesimally small theta. So what that means, when I have infinitesimally small, that goes to that d theta. So if I take that 1/2 theta r squared, area of a sector, and I add up an infinite amount of those, then we get this equation, and that's how you take the area of a function in polar coordinates. Okay, so we have the 1/2, the integral from a to b, and see our a and our b are theta values of r squared d theta. All right, and that's it, and you need to memorize that. That's huge. You will definitely have to use that. Okay, so if you're ever asked for an area problem, that's what you're going to have to use, 1/2 r squared. All right, so we're going to find the area that is enclosed by the graph of 5 cosine of 3 theta. Now remember, I told you don't have to memorize these. You will have a calculator, or the graph will be given to you. I'm just going to show you the graph really quickly so that we know what we're looking at. Okay, so here's the graph of 5 cosine of 3 theta. It's the rose with 3 petals. So I'm just going to do a brief sketch of this on the paper. So go ahead and do that on your paper. Brief sketch of this rose with 3 petals. It's going to look something like that. Okay, again, not perfect, but whatever. Okay, what we're going to do is, where you're going to start, you need to have kind of a brief understanding of how these work. So remember, think of the unit circle and where we start at 0. Okay, so this right here is most likely where we're going to be starting. So this is theta equals 0. And as I move around, this is going to move in this direction like this. You don't have to know this quite as well. I'm just kind of briefing you again on polars. And these should all come to a center point. All right. Another way that you could tell that that is where theta is starting, where theta equals 0, if you plug in 0 into my equation for theta, you get 5 cosine of 0, which is 5 times 1. So we're at theta equals 0 with a radius of 5, which would hit right there. Okay? All right, so that's briefly what my graph looks like. So I want to find the area enclosed by all of that. Now, what's going to be an issue is when we cross here, let me get a different pen. Well, as I follow this along and I hit here, that's fine, this is fine, this is fine, this is fine, until we hit here. Once we start overlapping ourselves on the polar graph, it doesn't really work out very well. Okay, so what we're going to do is the very first time that that crossed, which was right here, we're going to stop there. So if I were to find the area from 0 to that very first time I touch the pole, then what I'd be finding, and you can't look at it, see it in my graph, but what I'd be finding is the rose is symmetrical. So what I'd be finding is actually half of a petal. And if there's 3 petals, then I would be finding 1/6 of the area. Okay, and that's how you want to approach this problem, is that we're finding 1/6 of the area. So what I'm going to do for these purposes is I'm going to call this yellow region R. Okay, so if I want to find just the area of region R, that is not the total area, then let's just do that piece. So our polar is 1/2 times the integral from A to B. Well, our A is starting at 0, but what about our B? We want to look for when this is hitting the pole, or in other words, when R is equal to 0. So and actually if you trace that graph, that's going to hit 3 times at the pole. So we want to set our 0, or our R equal to 0, and solve for theta. So that is when cosine of 3 theta equals 0, or when 3 theta is equal to pi over 2, 3 pi over 2, and so on. So when I divide by 3, and the reason you want to do the so on, because as I showed you, you're going to cross through that pole 3 times, is because when you divide by 3, those thetas are going to now lie within 0 to 2 pi. So when I divide by 3, you'll actually get pi over 6, and then 3 pi over 6. So you also want to include, what would it be, 5 pi over 2, which would be the next value. So when you divide that by 3, you get 5 pi over 6. So that's those 3 values within 0 to 2 pi where that would hit. Okay, but we're only concerned with the first one, which is pi over 6. Okay, so the first time that that goes through the pole is at pi over 6. So that's going to be our B value. Okay. All right, and then of R squared, so that's going to be 5 cosine of 3 theta, the whole thing squared, d theta. Now, from here, we're just going to use the calculator. I'm just going to go ahead and tell you the answer. It's just 25 pi over 24. But remember, that's only 1/6 of the value. So the area of the whole region is equal to 6 times that, which, 24, which would equal 25 pi over 4, which is approximately, if you were to do it in decimal, 19.635. Okay? All right, so that's just a very brief overview of how to find the area in polar. Now we're actually going to do 2 more examples just so you can see how to deal that with the different types of polar graphs. Okay, for our next example, we're going to find the area of the region lying between the inner and outer loops of 1 minus 2 sine theta. So obviously this is going to be the one with the inner loop. So I've graphed it for you. It looks like this. So I want us to do a rough sketch of that on the paper. Okay, so again, like I said, very rough sketch. So it looks something like that. Okay, all right, so you see where it hits this positive x-axis again? That's going to be 0. And then over here on the negative x-axis, that's going to be pi. And then when it hits the y-axis, you're going to be at pi over 2 and 3 pi over 2. So if you follow this orientation, if you start at 0, it's going to go in this direction and then come around and go around like that. So when this hits the y-axis, we have the point here and the point here. So this is actually theta equals pi over 2, and this is theta equals 3 pi over 2. You don't really need to know that for this. I just want to kind of help show you how these polars work, okay? All right, so what's going to happen is we want to find the area of the region lying between the inner and outer loop, which would be that region there, okay? So what we would probably want to be interested in is when this graph hits this inner loop right there. So we need to find that value, which again, it's the same thing that we did before. We just want to know when that is going to equal 0. So we would set our function equal to 0 and solve for theta. So that's when sine of theta would equal positive 1/2, which would occur at both pi over 6, and that's the positive, so that would also be at 5 pi over 6. Okay, so the first time that it passes through, that's going to be at pi over 6. But then the second time it passes through, that's going to be at 5 pi over 6. Okay, so to do this, what I would recommend is finding the total area and then subtracting the area off of the loop. Okay, so first of all, let's do just the loop, or inside the loop. Okay, inside the loop starts at pi over 6 and ends at 5 pi over 6. So I'm going to use that as my bounds. So we have 1/2 from pi over 6 to 5 pi over 6 of r squared d theta, okay, which again, r is just the 1 minus 2 sine theta. All right, now for the outside loop, you don't want to start at 0, even though 0 is part of that outer loop. You want to, because if you start at 0, then you're going to hit the pi over 6 to 5 pi over 6, and you don't want to do that. So what I would do is I would pick up where you left off with that inside loop. So I would actually start at 5 pi over 6, which is where we're starting again with our outer loop. And so then 5 pi over 6 is going to carry around all the way. And now if I stop at 2 pi, that's not going to get me enough. I want to go all the way back to here. Okay, so this right here is 2 pi, right, if I start at 5 pi over 6. So then if I stop here, that would be pi over 6 plus 2 pi, which is going to be 13 pi over 6. Okay, so that's how I would do that problem. And that would be 13 pi over 6 r squared d theta. And then obviously the area that you want would then be the outside minus the inside. Okay, so I'm not going to do all the math there because you can just use the calculator and be good from that. All right, one more example, and that's finding a common region area. All right, so we want to, in number 3, find the area of the region common to the interior of these two graphs, -6 cosine and 2 minus 2 cosine. Here's what the graphs look like. So the brown one is the circle, the -6 cosine, and the blue one is the cardioid. Okay, so again, we're going to do a brief sketch of that on our paper. Again, I apologize for my very poor drawing, but it gets the point across. Okay, so the red is my cardioid. That's the 2 minus 2 cosine, and the blue is the circle. Okay, so what we want to do is find the area of the region common to the interior of the two graphs, which is that yellow area there. So if I start to calculate this, if you look at negative cosine of theta, it's actually, that graph's actually going to start right here. And that's at theta equals, sorry, we haven't calculated that. Okay, so if we want to know what that point is right there for the circle, we need to calculate what that theta is in order to put it into our integral. So that's at the pole. So what we're going to do is we're just going to set that circle equal to 0 in order to calculate what that theta would be. And so that's when cosine theta equals 0. So that's when theta equals pi over 2. Okay. So this is starting at pi over 2. And the reason that's happening is because it's the negative part of the cosine graph, and that's why it's starting at pi over 2, not at 0. Okay, so that blue graph, what I'm going to start doing is that radius, I'm going to start adding up these sectors, right? Okay, and then once I hit this intersection point, then that yellow region is now bounded by the red graph. Okay, so as I come out from the pole, it's now going to be bound by that red graph all the way until we get to the intersection point again. So what I can actually do is, this is not according to my graph, this is a symmetrical graph, so I'm actually just going to look at the top half and then multiply by 2. Okay, so what we need to do is we need to find, obviously, since we're looking at the common region, we need to find the point of intersection right here. Okay, so to find that point of intersection, we're going to set these equal to each other and hope that they're simultaneous points of intersection. All right, so to do this, I would add 2 over, so that would be negative 4 cosine theta equals 2, so cosine theta equals negative 1/2, and theta would then occur at 2 pi over 3, and also at 4 pi over 3. That's going to happen down here. We're really only concerned with the 2 pi over 3, but that's okay. All right, so at 2 pi over 3, this yellow region is bounded by a different curve. So we're going to start off with the blue, the circle, and then we're going to end with the red, which is the cardioid. So again, we're only going to do half of this at a time. So my first thing is I'm going to do half the area of the circle. Okay, so half the area of the circle is going to be, I'm going to do this in blue, is 1/2 of the integral from, we started that circle at pi over 2, and we're going to end at that intersection point of 2 pi over 3 of the circle's area, or radius, squared. So the circle's r is negative 6 cosine theta, and that whole thing squared. Okay? And then we can also find half the area of the cardioid. So half the area of the cardioid, now that cardioid is going to pick up at that same 2 pi over 3. And then where would it end? That half would end. That would end right here at, it should be pi. So what I would do is I would check to make sure that that's pi. So and so what happens is if you get a positive value, then that means that you're at pi. So if you were to plug in pi for cosine theta here, cosine of pi is negative 1. Then times negative 2 would be positive 2. So 2 plus 2, you would get 4. So since you got a positive radius, that means it's in the direction of pi. So that is for sure pi. So then your area of your cardioid would go from 2 pi over 3 to pi of the cardioid equation, which is 2 minus 2 cosine theta squared d theta. So then to find the total final area, the total area would be 2 times that half area of the circle plus that half area of the cardioid. Okay, so again, you can use the calculator to do that. All right, so that is how to find the area of polar graphs.